D8, D8 is going to be the weight, your weight, at the poles of the Earth and the equator. So let's first of all consider the North or South Pole. So we'll first of all consider the poles. Here we have the Earth. And we could put in here, say, an axis, another axis. So here we can consider this the y-axis going up and the x-axis here, and the Earth, say, rotating, going around like this with some omega. Now, the Earth, due to the rotation, has a little bit of a bulge, and the radius at the equator is not the exact same as the radius at the poles. The radius at the equator here is slightly larger. So we'll say the radius at the equator slightly larger than the radius at the poles. All right, so we want to put ourselves at the North Pole, say. We're at the North Pole, and here I'll put a little box, that's us. And if we look at this box, let's enlarge the box. This is the person, all right, it's a box. Then you see for the center of the box, there is the mg force. This is the force due to gravity pulling the mass down. But since you're sitting on the Earth, there's a normal force of the Earth, the ground, is pushing you up so that you don't penetrate into the Earth and you don't levitate. So there's a cancellation of the forces. So the mg is the weight. Now here, since we don't experience any, let's say if you were on the Earth, you wouldn't experience any centrifugal fictitious force because the radius is 0. Remember, for the centripetal force and its opposite, centrifugal force, the r is relevant, and since r is 0, the radius away from the axis of rotation is 0, that you don't experience any of those forces. You just experience, say, the gravity and the normal force going up. So if we look at this, we can write an equation that mg and n cancel. So I could say the normal force going up minus mg going down is equal to 0. And the normal force is equal to mg, and you can think of the normal force as what the scale is going to read. You're standing on a scale, so the scale is pushing you up, and the scale is going to give you a reading of what your weight is. So what's relevant here is the forces in the y direction, and in some books they'll say the sum of the forces in the y direction equals mass times the acceleration in the y direction, but there is no acceleration in the y direction because the rotation is this way, and the acceleration would be, say, if you were here at the equator, it would be inward. So since this is 0, the force in the y direction is 0, and the force in the y direction would be your normal force going up minus the mg going down equals 0. So, two forces. Now, G is 9.8 meters per second squared. And if we have a mass, say for a mass of 100 kilograms, then when you multiply the 100 times the 9.8, the force that you're going to get here is 980 newtons. Now we go to B. What about at the equator? Well, we can consider a similar diagram. There's the Earth. There's the y-axis, and we're going around the y-axis with the angular velocity omega. And we come out here, the x-axis. But now the little block is sitting on the equator here, and we're going around. So now, if I take this block and do this, the mg is along the negative x-axis. So here is where the mg is, going this way. And then the Earth's surface is holding you in place by pushing the force this way. But now we have to worry about something else, and that is, since we are undergoing an acceleration, we got to bring that acceleration into play. So to be very careful, we can say that some of the forces in the x direction would be the normal force pushing in the positive x direction. Remember, this direction here is positive x. And then we have minus the gravity. But see, this is equal to ma, and the acceleration in the x direction is not zero. In fact, there's centripetal acceleration pointing in a negative x direction toward the center. And that's going to be here minus mv squared over r, where r is the radius of the Earth. Let me just go ahead and call that big R for now. Then remember that if we write this out as minus m, this includes the m, so the acceleration is the minus v squared over r, but the m is included for the force. So you have m times v squared over r, and now we can use our formula. V is omega r, and replace this v, and we're going to wind up getting what we had earlier, m omega squared r with the minus sign. Well, let's go ahead and do it again. So this force, some of the forces in the x direction is going to be minus m omega squared r squared over r, and that's going to be minus m omega squared r. So now you see that we have this other feature. And if we look at this equation, just clean it up a little bit again, n minus mg equals minus m omega squared r. You can see what the scale reads now is going to be a little less than mg. Let's go ahead and solve for the scale reading. That's going to be mg minus m omega squared r. In other words, you're going to weigh a little less. And if you're standing there, you could say, although physicists don't like to say it this way, that throwout force eases up on the scale. But the correct way to look at it is from outside, with all these forces as expressed from the outside observer, which is the inertial frame, the frame that's not accelerating. We're looking at analyzing the problem. Now, often for the omega for the Earth, you see a capital omega like this. the angular velocity. But what I would like to do now is write this in, this scale force, as mg, and then factor out the mg to have a 1, and then minus omega squared r, and then you would have to put the g down here so that when you multiply mg in, you get your mg, the minus sign, and then the g's cancel. You get m omega squared r. This is showing explicitly that the weight at the equator is a little less. The question is, how do you figure out this omega? Well, omega is 2 pi radians, go all the way around, divided by the time that go all the way around the Earth. Well, or the Earth to rotate once. So that point there, if you're standing there, you go all the way around in a rotation once each day. So now we have this one day. This is going to be 2 pi over 24 hours times 3,600 seconds in an hour. So now I have radians per second. And if you work this out, you're going to get, for the omega, 7.2722 times 10 to the minus fifth radians per second. We don't usually write radians in, since radians technically has no dimensions, since if you look at your formula for radians, S is r theta, r is in meters, the arc length is in meters, and then this is dimensionless. Technically, the radians is given by taking S divided by r, and the meters cancel out. So then you need the radius of the Earth, and the radius of the Earth here, because you have this omega, you then need to put the radius of the Earth in. So that's going to be equal to 6,371 kilometers. And when you put this in, and in the book that's at my website that goes with this, you find out that you get, for all this stuff in here, you get 0.0034. And if you want to think percentage-wise, where this is 100%, you move the decimal over 2, and you're going to get 0.34% less weight. Now that's not much, right? So if whatever you weigh, you basically are going to be subtracting 0.34, percentage-wise from your weight. Now that radius I use is considered a kind of average value for the Earth's radius. If you use the actual radius at the equator, then you find that the radius is a little larger at the equator than at the North and South Pole, and that corrects things, and this becomes 0.51% less weight when you have the more precise value for the radius rather than some kind of average. You're actually using the value at the equator. So this is the one that's the correct answer. So it's about 0.5% less at the equator due to the bulging effect. And the Earth's not a perfect sphere.